Hello, thank you for tuning into this video focusing on SQL methods for data analytics. So what is SQL, or Structured Query Language? This is a special purpose declarative programming language. Its primary objective is to define, manipulate, and retrieve data stored in relational databases. Now, so it's not really a standalone tool, but a featured set of a corresponding relational database system. And with SQL, its actual core language is maintained with by the ANSI standard, and so it really is an industry language used across many platforms. In addition to that, many dialects actually extend that core language. And dialects being Oracle, Postgres, Redshift, Spark, you name it. Any type of database that runs SQL, and this is really one of its primary great features in that interoperability across platforms. And with all that, SQL really has traditionally been used in software development and IT infrastructure, maintaining repositories for a lot of organizational data. But it's now really emerging in the data science analytics space, and no doubt just owing to the nature of the work. We're now in big data, cloud computing, centralized platforms that no doubt a data analyst and data scientist today will be talking and integrating their operations with a sort of back end system. And really, using SQL in this environment really carries forward a lot of advantages. SQL is a readable, maintainable, expressive, stylized type of language that really follows the sentence semantics of human language, namely the English language: select, from, join, where, group by, order by clauses. And so it's really great in that initial front that many can really newcomers can really attach to very quickly. SQL also is a very fluid. It can be, again, it's a special purpose that can be layered in application code such as Python. And so just for that reason, it's a great complementary tool. And as mentioned earlier, it's transferable across platforms. You could run the same query within a Python environment into an R environment, into a Java environment, a C# environment, and so on and so forth, and even in various IDEs or command line tools. SQL can also can be arguably more efficient in a lot of data analytic operations because it follows a set-based logical order of operations rather than the lexical order where code is run in the order it's written in. And then it also is integrated with a query optimizer, so you can actually efficiently optimize, refactor various aspects of your code and set up indices to really add performance to a lot of operations. And then SQL scales to big data platforms and repositories. Again, that's its primary focus is the relational database, data warehousing aspect. And as mentioned earlier, it can be used as a complementary tool within the data pipeline, doing a lot of the heavy lifting. A lot of people make the comparison Python versus SQL. But really, it should be Python and SQL. You can really use both together in the data analytics space. And so I hope to really use this video to show many of the advantages of using SQL in the data analytics space. The example data I'll be using would be from the Botanic Gardens Conservation International, BGCI, based out in London. They're an international organization that really promotes and focuses on the biodiversity of plants worldwide. And among many of their other initiatives, they maintain a plant threat assessment tool where users could, go to that portal, pull up by family, by genus, by species, the assessment statuses of various plants across various years. And so I did just that. I pulled that very large database, mined that tool, and in imported it into an SQLite database. SQLite will be the relational database for this example. It's a very rich, expressive RDBMS, and it's actually a very different than many of the traditional relational databases, and that it's a file level, where the database sits within a file directory rather than being a server level, enterprise level. So for a lot of small scale operations, this is a great tool, and and certainly for a lot of database data analytics teams can really tap into. So one great example of using this BGCI plant threat assessment database is just data organization. SQL allows you to do very, sophisticated things with just their select clause, the most popular probably clause of the SQL language. You can order your columns accordingly. You can name, identifiers for short names, and set, so the a lot of the formatting can be handled in the select clause. This is a very simplified version, where we're pulling from that one table and then we're showing the first 10 rows. So a quick output of that simpler statement, but then it certainly could be extended. One great aspect of SQL, it has a rich repository of string functions, basic arithmetic operations, and you could do even conditional logic, even nested, to very sophisticated needs. So here, this is one, column, I'm deriving from the plant name. I'm essentially cleaning the plant name of the last two, the ending of the original raw name, retaining only the first two identifiers for a nice cleaner set. And so I can do all of that within the select clause, in one aspect. So again, traditionally in Python Pandas, NumPy, we have to do a lot of multiple steps to do a lot of these cleaning. You can do this within one statement across many columns, in a very clean, easy to read setup. And then you could do case logic, logical operations. If that interpretive conservation status is data deficient, clean it out, make it a missing value, or return that non-missing value. Let's add a study year, all years comparing to its first year, 1970, and so on and so forth. So you can really, and then substring, so you can do a lot of string and number manipulation very cleanly and easily. This will require multiple lines in your application code. SQL streamlines that. Set-based operations. This is working off of the set theory of mathematics. SQL really sees data relations in sets. And so this will be great for a lot of cluster grouping operations, sampling operations that you want to compare between. You want to look at values between. You want to join, merge unique, deduped values overall. So what we're going to do here is we're going to look at the geographic scope within the not threatened and threatened categories of our plan assessments. I'm going to return the distinct geographic scope in one set, and then I'm going to union it to the second set, and return all unique values between both, as a union clause, similar to the mathematics terminology. However, we may want to just look at where they share the same geographic scope, and we can here use the intersect. Specify our same first set, our intersect clause, and then our second set, and then get now a shortened list that's really the shared commonality geographic between both sets. Then we can even go further. We can then look at what's in one set and not the other. And this we'll use the except clause. And this is where order matters. Here we're looking at the threatened, what's in the threatened list that's not in the not threatened list, using except clause, and then we get a shortened version of that, and then similarly vice versa, do likewise with except, but this time look at what's in threatened but not in the threatened list, and get that output. So as you can see, this streamlines a lot of aspects, and really there's certainly a lot of synonymous, analogous ways of doing this within the Python application library, but this allows you to do it with the SQL in a more simplified and easy to read setup. Combinations, permutations, pairing. This may come in when you're setting up longitudinal panel studies and you need balance. Then you have challenges of unbalance. Some years are showing up, some groups are showing up in certain years, but not others, and you need a complete set. With the SQL language, again, going back to that set-based aspect, is many of its extensions of the join. SQL has the cross join, which is a Cartesian product between both two sets. And then the classic inner join, left join, right join, and the full join semantics. But here we'll use the cross join because we want all combinations between the major plant group and its assessment year. And we'll use this as sort of a base that we can then join with our data so we can complete a balanced setup. And so we're returning the distinct values of major group, distinct values of assessment, and cross joining the two. We'll clean out any missing values and get a nice long, pairwise setup of all combinations. So again, SQL allows that easy setup within its language construct. Aggregation. This is a very popular and very probably useful aspect of SQL in data analytics, where you can really return summary stats and diagnostics very easily and quickly with SQL. One great reason is because you can set up multiple groupings and multiple aggregate functions really in one compact statement. Here we're going back to our plant groups, our distinct four plant species groups, and we're going to run several aggregations and even a sophisticated one, count distinct. So let's return all distinct family, all distinct genus, a full count of all plants, the min and max assessment years. And so we can run those aggregations by those groupings and return a nice set overall. Again, you can do this in pandas, NumPy, but it'll be a very dense type of call rather than this compact statement. You can swap out the groupings. This time where you look at our statuses, our interpreted conservation status, run the same aggregates across. Then we can do multiple groupings. We can extend the group call for both major and interpretive conservation status, and return those values overall. And you probably will see the similarity of pandas' group by with SQL's group by, showing you that they really retain the same type of operations overall. You can even do nuance aggregations. Here's is a popular conditional aggregation. Usually this is used to reshape, pivot your data for presentation purposes in a wide format. What we're going to do here is we're still a count, but a conditional count. We're going to look at all the plants, all rows that follow in 2015, 2016, all the way to 2020. The threatened list. We can even run a condition within our aggregation, and then we can pivot accordingly by our grouping. So as you can see here, we get a wider format by year. Certainly, we could have just added assessment year as a grouping, but that would be a more longer version, a little harder to read, rather than this nice compact overall report table. Similarly, just we can swap out our conditions. This time, let's look at threatened and not threatened, and even throw in an original aggregate, a non-conditional aggregate, so and set that up. Again, the sophistication that we can do a lot of operations within one compact statement is really the great aspect of SQL. Advanced SQL now allows us to even do more sophisticated operations. In the latter versions of ANSI SQL, it came to common table expression. This came in the SQL 1999 standard, and the window functions, which came a few years later in the 2003 standard. It was only until 2018 SQL integrated it into their core code. So SQLite now can, its latest version can run common table expressions and window functions. Common table CTEs essentially is just an intermediate. It's specifying an intermediate data object that's then used in the final result set. And you specify that with the with clause. So what we're doing is actually setting up our original aggregate function result storing that in an alias called sub, and call sub in the final statement. And this, you no doubt will know that this is sort of a helper object. We had to do that a lot in pandas and NumPy, where we define another object that's then used as an intermediate to our final data analytics needs. And so this can have very usefulness in a lot of data science operations. And then once we set up our derived data source, we can then run our sophisticated window functions. This is essentially the best way to say is an inline aggregate. You retain the same rows, but you're really running aggregations across rows. It's defined as setting up an aggregate function with the over clause, and then within the over clause, a partition by if you want to do it by groups, and an order by if you want to run across rows. So here, what we're going to do is we're going to look at all of our interpreted statuses within the groups and set up a rank variable. See how they come out by their count of plants overall in descending order. And so here, as you can see, within the groups 1 through 5, and we can see which categories arrives at the top. Mostly it's not threatened, but gymnosperm shows a threatened was the number 1. And so we can see how that comes out. We can do an inline aggregate. We can sum across count plants across all of those major groups, and as you can see, they repeat for each of those groups. And then even with that, we can even set up a percentage calculation. How does not threatened within angiosperms play out? 38, 39%, and then so on and so forth for the other groups. So again, you can do a lot of and no doubt you'll need this, and have done this in a lot of analytical operations. Then we can even do a running sum by specifying an order by a clause within that sum partition. So and this can have many needs: running calculations, lead lag variables, because window functions are also deemed as analytical functions. Moving averages, year over year analysis. Anytime you need to look at intervals across rows, forward or backwards, window functions can really help, and then certainly by size by your various groupings. And then finally, just showing you yet another sophisticated advanced level setup that you can do with SQL very easily, that can't really seamlessly or compactly be done with application tools like pandas, NumPy. Here's the interval, lateral, or range join. No doubt with log files, event time studies, tracking data, there's always two sets that you can't merge on a discrete value. You sometimes have to merge across intervals or within subset filters, and so running across a window. And so SQL really handles that pretty nicely. Again, we're using a common table expression. We're specifying an intermediate data set. What we're doing here is actually a full join. SQL doesn't support the full join. Other databases do, Oracle, Postgres, SQL Server, but in other non-enterprise level, you'll sometimes it's more long-winded that you have to write your SQL. But here we're doing a left join and a right join. Actually, even a self the right join isn't supported, but I swapped them out, P2, P1, rather than P1, P2. So, and then union the two sets together to get a full join. And what we're doing here is we're going to do a side-by-side comparison of the 20th century count of threatened plants and the 21st century count of threatened and not threatened plants, and seeing how that plays out. But one thing I want to really show you is doing that range join. Now, in a lot of these type of joins in current operations, we have to first merge first and then do a subset. That can be very taxing on very large data sets. SQL allows the join to take on any Boolean logic So you can really merge at the same time you're doing your interval, lateral, range type of needs. So this is where I'm specifying the P1 take only the data for assessment years before or equal to 2000, and then P2 on or after 2001, and then joining those two sets together with that. Again, in other languages you have to do intermediate objects multiple and then join them together in your final result set. SQL, again, this is one, as dense as and many aspects that it is, this is one statement. Even though there was multiple selects, you saw common table expressions can't be run on them just by themselves. They need a final statement. And you can even extend this to multiple CTEs, comma separated, to really render a final result, be a very complex, very simple aspect. So overall, I hope I was able to really, give you a preview of really a lot of the advantages that SQL can have in data analytics. Again, maintaining a very compact, readable, sentence-like structure, semantics. You can do a lot of very efficient operations with intermediate final result sets, joining in many very nuanced ways. So really, you use SQL as a really advantageous tool within your data pipeline. Again, it's not a substitute for Python, NumPy, but can really be an additive. At least first, sourcing the data, compiling it for your final plotting, modeling needs. So thank you again for tuning in, and I hope this was very helpful.